to talk about beer and caipirinha in the dinner tonight. She will talk about water. It's more appropriate for this time.
For the talk,
right?
for the talk.
For the talk.
So I would like to start by thanking the organizers for the possibility of being here in Natal, that wonderful city. And I start with this photograph. That's not a cartoon, it's a photograph and taken by Clóvis Jardim, a friend of mine, not in Brazil, of course. This was taken in Patagonia. And I actually do love water, because water is the only material in which you can have a laboratory in plain sight here, because you can see solid, liquid, and if you really force your eyes, you're going to see water vapor. So we can see everything in your planet. So I just love this material. So the talk is going to go as follows. What's the mystery? Because in life, I love to look for mysteries. So there is a mystery. Why should we care? Because there are many mysteries that I confess I don't care. I don't know who brought this glass of water here, but I don't care. But there are mysteries that I do care. I'm going to convince you that there are mysteries in water that you should care about. Then, as a detective, you go for clues to solve the mystery, our results, and finally I'm going to try to bring some conclusions. But before that, I want to introduce all the main actors of this big theater that's science in my lab, so it's my research groups, and a few collaborators from other places. Okay, so what was the mystery that dragged me? If you take water and you flow water through carbon nanotubes, you're going to see that the difference between what you measure as flow and what you're supposed to measure if you believe in the hydrodynamics would be up to 900 times. I don't know in your country, but in my country, when a student gives a result that's 900 times different than they should have, there is a mistake. So I was looking to that, and I also found that was fascinating that as you shrink the nanotube, you have these kinks, the kinks that are different temperatures, but there are kinks. So that's an experiment. So that was the fascinating thing for me. Okay, what is going on in this kind of nanotubes that make water flow so fast that fails hydrodynamics? Okay, but before going to that, I should convince you that water matters. And before, if you take all the water, move all the water off the planet, something that I think Nestlé wants to own, but doesn't. So you take all the water off the planet, and you put in a tube like that. 97.5% of this water is salty water. And this little cover here, that I enhance here, will be non-salty water. Then most of the salty water will be frozen. Okay, that's frozen water, that moisture. That's water underneath, like you have in Brazil, kilometers and kilometers of aquifers. That's underneath water, hard to get. And that little things, the thing we have been easily live. And in Brazil, we have plenty of that. So we have a lot of water, but not most of the water is kind of harsh. We have either to take the salt, we have to melt, we have some capture from the air, and you have to give 1 kilometer down in order to get the aquifer. So it's hard, easy water. Okay, have plenty, but it's easy. But is this enough? Because maybe this is little compared with the other parts, but it's enough forever. So what UN did is that they account in the planet for the regions they have enough water for living and not enough water for living. They call that scarcity. So if you go red, means that you have less water than you need to live. And if you go blue, you have more than enough you have to live. And that's a 1950 picture of that. You see that already in Africa, in many places, they have less water than they need to live. Don't get scared, people from Europe, because you actually don't produce your food, so you do not need that much water anyway. Okay, so you're using other people's water. So, but if you times pass, you're going to see that our planet is getting red, and that's not a political statement. Actually, I believe in that the planet is getting blue. But anyway, so it's getting red and red, and the prediction is that in 2025, that's very close by, half of the planet will be in scarcity. Okay, so we have a problem with water. Okay, with the easy water, not the difficult water, with the easy water. So with that, I think I'm pretty convinced you that we need to study water. Then people will say, well, let's save water, please still take showers, and there are many other ways to keep. And if you want to see how to save it, that's again is the surprising thing, because we love to blame industry, we love to do that, because it's the others, you love to blame the others. And we try to save in domestic households, but if you really want to save water, you have to starve. It's the better thing, diet today for saving water for tomorrow, because food is the place where you have been using more and more water. And we have a very good example in Brazil. Remember, Brazil in that map was blue all over the place. However, a few years back, we have lack of water in São Paulo, major, richer part of Brazil. And the reason is that we start to plant like crazy sugarcane in São Paulo. We plant sugarcane not only because we love sugar, but because we are producing ethanol for our cars. And that was growing, and sugarcane is loves drinking water. It's a plant that needs a lot of water. So we end up having a problem of distribution in São Paulo because of this food. Okay, so we have to plan for water. But before going to how we are going to manage that, we have already in the planet a number of ways to desalt water. Unfortunately, these methods, that is distillation, reverse osmosis, they are expensive, and they are almost in their thermodynamic limits. And the reason is that those methods, they don't use anything that's particular for water. You know, reverse osmosis is filtration. So you can filter water, you can filter whatever with this mechanism. You just have to have the holes small enough. So we are not using water have that is better than other liquids. Okay? It's just using something normal. Distillation is just to heat water, make vapor, and then liquid again. Again, you're not using something that water gives you an extra, a special, something that water would have as a special property. And water have a number of special properties. Actually, today, it has 74, and I may be mistaken because I didn't check the computer right now, because this number keeps moving up. 74 things in which water does different from the others. But we are so surrounded by water that we think that's trivial, and it's not. I'm going to show a few examples in which water is special, and sometimes you don't care about. One thing is the specific heat. I'm just plotting here, sorry for the small sign, this is specific heat against temperature for water. And then example I'm showing here for methanol. And the thing that you notice is that both in a certain range increasing with temperature, but water have this overturn here. But more than that, water have twice the specific heat of methanol. And that's a great thing to have this huge specific heat. It's great because it makes a very good heat balance for the planet, heat balance for us. So it's a very good property to be different. So it's different from the others. Then you have this funny minimum that tells you that there's something very strong and different going, and it is up. That looks like a divergence. If you go now to the compressibility against the compressed water, and most materials, here I'm giving Tolwyn for a number of pressures, and you see that most materials goes up the compressibility as you increase the temperature. But for water, it goes up for a certain range, but it goes down again. I might make you notice that all the minimums are in the region where we live, in our range of temperatures, so the weirdness. And if you look to the compressibility, different from the specific heat, the compressibility of water compared with other liquids is quite small. And that have a number of good things, means you get more land, because with all this water covering the planet, if the compressibility would be this size, water would spread more, but also have some bad things. It's the tsunami one of them, because the wall of water moved almost like a solid in the ocean. So there is another weird, and again, this weird minimum. Then there's a thermal expansion. That's something you know much more, because this is what leads to the maximum of density. So water, unlike the other materials, you have a region in which you decrease the temperature, and water decrease the density. So instead of going like that, as you decrease the temperature, water goes like that, and then do that again. And that's very important. It is really very important, because that's what's make when you go to a place that's not Brazil, and you have a winter, you have the top of the lakes covered with ice, but not the bottom. So ice have a lower density than water. Okay, so that's what makes possible to have water. It makes life, creating life. And today, people aren't any longer looking for extraterrestrial, like with green people, but they are looking for bacteria and virus in the planets or in the satellites that are covered with ice, because they think underneath there will be water. And there will be water because we have this density anomaly. And you might say, okay, who cares in Brazil with this density anomaly, because we don't have snow, we don't have ice, we don't have ice fever. But I might remember that at some point in our story, we are all covered with ice. And people believe that life started just in one of those moments in which underneath all this huge amount of water. So, but there is a much more interesting property of water that's quite related with my first mystery, is that diffusion. If you now take water and you compress at very low temperatures, instead of having a diffusion constant that is going to increase when you decrease pressure, is going to decrease. What means that you compress, you put more water particles, and they are going to move faster. You know, more particles, they move faster. Okay, so that's the mystery. And part of this mystery you can understand on basis of the hydrogen bond. So you have a water molecule, a cartoon of a water molecule, and another water molecule, and they can make these hydrogen bonds. But because the hydrogen bonds are related to the dipole moments of water, they require a certain distance. You cannot be, make a bond if you're too close, because you don't see the dipoles, you see the charge. And if you're far away, you add up the two charges and you don't see anything. So you need a certain distance to form the hydrogen bonds, and water can form these 4 hydrogen bonds on that. So water will be a mixture of non-bonded with bonded. And as you bond and you do that, that explains why you may decrease the temperature, you make all bonded, so you kind of increase. But even the drinking water, you should respect, you look to your drinking water, you're going to imagine a lot of these bonds dancing around, and is this competition that leads to the most anomalies of water. Means if you look to the specific heat, remember that I have this huge increase, I also can write the specific heat as the entropy fluctuation, my local entropy minus the average entropy. And if you imagine water being this mixture of a local, very structured and full of hydrogen bonds, but when you mix, they kind of get disarranged. You can understand why when you decrease the temperature, you have these clusters of bonded water being formed, and it explains why you have that huge increase in the specific heat. The same applies to the compressibility, because the compressibility is the difference between the local volume and then the average volume. So you can again think that you have a very large local volume and a smaller because you break the bonds. And finally, the alpha is the cross of that, and because one goes up and another one goes down, you have this minus, this negative sign that explains the density anomaly. Of course, this explanation in the tips of my fingers is beautiful, but it's not good enough. So many years ago, we decided to look to these properties using a model of water. You can take your favorite model. At that time, I took SPCE, and I did molecular dynamics simulations of that. What we found is that really the water have this diffusion anomaly. It means that I increase the density and I could see the increase of diffusion constant. So I increase the density and the particles start to move faster. I remember at that time I was very happy. And I went to my mom. Usually I tell all the things to my mom. I did that great thing. I found the same thing as the Austin Angel, the experimenter, found. And my mother said, but if the guy found before, why you are looking to that? What's the novelty of finding something that the other guy found? I cannot understand that. So I told her, I can do one thing this guy cannot do. I'm going to put an arrow, and I'm going to look to the molecules doing that. Understand? Because water needs to do the bounds. If it's moving faster, I start to think maybe this breaking the bounds when it moves. What's the mechanism? And I can look to the mechanism. So we decide to look the time to do that. This is the time to rotate. So if it's more times to rotate, less times to rotate. And we found that at that region where you have the maximum of diffusion, the things has less time to rotate and have more time when you have the minimum of diffusion. What means that the water is not doing like that in principle, but on average is also doing like that. Okay, so it's moving faster and is rotating faster. But that is more fascinating because at the same time, another group, the Stanley's group, they look who was moving faster and who was diffusing faster. And what they found is that actually the particles that move faster, the water particles, are not the one rotating faster. The ones that are moving faster are the neighbors of the one rotating faster. Okay, so it walks like that. Walks and the sides rotate in a way that they don't break the bonds. Okay, so I want to form a bond here. He's not going to rotate, please. He's going to rotate to make the bond. So I move again, she rotates, and go on rotating. But I start to be very puzzled with this mechanism because on average, I went to my collaborator, Paulo Netz, and said, Paulo, what's going on? Because even to move like that, you don't have space to keep all the time 4 bonds. How is keeping the 4 bonds? And he measures that it's keeping the 4 bonds. Paulo Netz's German family tradition, very strong, said it's keeping. I review all the calculations. So I told, let's look to the number of neighbors, because maybe it has more neighbors to keep the bonds. He said, no, that's impossible. So we look at that. And what we found is that in the region in which you have the maximum diffusion, actually the water molecules have the 4 normal and traditional ones that should make the bonds, but also have 1 or more neighbors that are there. You understand, the friendly friend that is there, and when you need a hand, makes the bond. In that way, it could keep, even moving, keep the bonds, increase the density because we have 6 neighbors, and jump from one neighbor to the other. Quite a promiscuous molecule. Okay, so we could see the 2 mechanisms, and we could understand how water was moving, trying all the time to keep the bonds. I was not in that, these things, bonding, non-bonding, this dance was a very important thing. So I thought, let me test if this is the key mechanism. In order to do that, I did the following. Let's take the tetramer, 1 water, the 4 neighbors, and let's call that 1 particle, okay? Forget the bonds, hydrogen bonds. Let's take the tetramer. Let's integrate back using the radial distribution function of this, okay? And make spheres in a box with the potential obtained for integrating back all that. So now I don't have the hydrogen bond. Throw away. I put that in an effective way inside my molecule. You see? So gone oxygen, gone hydrogen. I just have spheres, but these spheres interact with other spheres using the OO obtained in this real water SPCE, that's that, integrating using hypernet chain equations. You can use whatever, and you obtain a potential that's like that. this potential means that I have one scale that will be the bounded scale, and another scale that will be unbounded scale. We have a number of options because depending on the type of Ethernet chain you use, you have little variation, but you always have the two length scales, okay? So I went back, I did again molecular dynamics. Now, no oxygen, no hydrogen, just the spheres interacting with each other. And what you find that actually you have the density anomaly, the diffusion anomaly, have all the bunch of anomalies, and you have even the second critical point. That's another topic for itself that some people predict that exists in water. And if you change, we test a number of potentials, and most of the potentials, they do have the anomalies. The only one that didn't have is when you make any of the scales too deep, okay? So I said, wow, let's try to see in these two length scales potential, which ones are the good ones that give the anomalies of water, which ones are the bad ones that don't give. And to do that, what we did is that we sit in an isocore, okay? And we move and look to the radial distribution function in a potential that have the anomaly and compare with the potential that doesn't have the anomaly. So when you have anomalies, usually instead of having one first peak, you have two, because you have two length scales. So if you take your favorite Leonard-Jones, you're going to have one peak in radial distribution function. Here we have two, and if you've changed temperature, particles you move from one to another. So increased temperature, this peak goes down, means the particles you move from one peak to the other peak. And if you change the potential, that will be true whatever you have a potential that have the anomaly. When you don't have the anomaly, the particles don't move because the potential is too deep in that length scale, and particles get trapped. And you don't have this beautiful dance of making bonds and breaking bonds, even though this potential don't have hydrogen bonds, but they have the two length scales. So the two length scales are the way to have these anomalies, that what they call volumetric anomalies of water. Okay, that's the summary of that. Okay, that is for bulk water. Now let's confine water in nanotubes. Remember the problem of having this fast-moving confining water. And one thing people observe is that when you decrease the size, this is diameter of the nanotube, the diffusion coefficient goes down, and then if you decrease a little bit more, it goes up again. So in water already in the diffusion, that's not the flow that I showed you first cartoon, it goes down and up again, okay? Also, when you cut the tube, water is not going to be uniform, but will be layered. So this is a tube, it's cutted, and you have this peak, so we find water close to the wall, nothing in the center. Then you make a larger tube, you start to form layers and layers and layers of water, depending what type of nanotube you have. So what do you decide to do? Let's check if this very naive two-length scales potential that we have is able to capture that and to learn something else. Because remember, in our model, we don't have water molecules. You have tetramers. So we're much larger, what allows us to see better the layering. So we did that, we make a tube, we have two reservoirs. What you do here is that you do a grand canonical Monte Carlo in both sides, and inside the tube you do molecular dynamics. So you keep temperature using the grand canonical Monte Carlo. We keep the two with the same chemical potential because you just want to see diffusion. You're not going to see flux at the moment. Okay, so we do that as this combination. We use our two-length scale potential. We even try a number of potentials for the wall, but that doesn't important. The importance that we, as you shrink the tube, you again observe the same decrease going down and increase again. Let's see if I'm lucky enough to have the videos that I have here working. So that's the huge tube. That's a tube that was cut. So you can see there is no diffusion because the chemical potential in both reservoirs are the same, and particles are moving. This is a tube that will be 4 times, the radius is 4 times the size of each one of my spheres, but they are moving pretty well. Then I decrease. Then I decrease the size, and things get stuck. You know, this is not the freezing temperature for my potential. That's far away from the freezing, but particles get frozen inside simply because they are in the minimum of the potential. If you make the wall potential particle, they just get stuck. Okay? They stop like the down I show you both in the experiments and in my simulation. So, but then if I squeeze a little bit more, okay, particles move again. And they form a very interesting thing that is they are kind of lining from time to time, but they have space enough to 2 of them be there because one pass over the other. And that's just the diffusion, and they are very quick, but they have this tendency of being aligned because aligned they are in the distance of what would be, in my model, the hydrogen bond. So we observe a point like here for, a point like here, and then when it goes again, it just compare the real deal with our results. Our results are all in dimensionless units because it's just an effective model. And when you cut our tube, we again observe all this layering that was observed in the experimental results. Let's come again to talk about the flow, okay? So remember, I told you that I have a flow, and I decrease the size, and here it's calculating the enhancement factor. That's the experimental result, and in my system, what I'm going to do is to do the same things. But now I'm going to have a different chemical potential here, so the particles will move from one side to the other of the tube. I'm just going to play around again with my potential to length scales. I can make it more attractive or less attractive because it's effective potential. Let's now try to explain what this enhancement factor means, both in the simulations, in my calculation. If you want to calculate the average velocity in the flow direction, that's proportional to the difference in pressure and the length of the tube. And this proportionality through the hydrodynamic equations depends on the radius and viscosity, and you always can relate viscosity with diffusion. So if you calculate diffusion, you have temperature, you have sigma, you have the size of the tube, you have the length of the tube, you have delta P, you have that. But then you measure the velocity, and you have the delta P, and you have this gamma. So this enhancement factor is the ratio between what you got from the molecular dynamics to our experiments and what you should have from the hydrodynamic equations. Now we did the simulations for different size. Again, I'm doing that, and you can see the layering, and you end up with that single line that I already showed to you. It will be changed a little bit or more if you make the water-water interactions more or less attractive. If you make less attractive, you have more layering because the wall forces a certain organization in your system. Then you can compute also the time distribution to pass through the tube. That's for different radius of the system. And when you make the water less water-water attractive, you realize that part of the water in the wall will be running different from the center. That's something is already observed when you take cellulose and you freeze water and then you defroze water. You see that some of the water get attached, even if the temperature is beyond, hotter than the frozen temperature, melting temperature of water, some of the water is going to keep on the wall and not leaving because it's frozen in the wall. So there is some attachment in the walls. And that's our enhancement factor. You observe that as you squeeze, as decrease the size, you have this going up, down, up again. Here's for simply for different potentials. And again, you see that when it goes down, the kinks that I showed you before, they were related to change in the number of layering. Okay. So there was a change in the number of layering as you decrease the system. Let's see if the movie works well again. So that's, again, the larger tube. And you can see, and in this case, I'm making the particles, the potential that's attractive. And because they are attractive, they try to keep the side hydrogen bonds quite fixed. And that's the layers, they flow like layers. They are not moving too much like that. So they flow like they are hand-to-hand doing that, using the cover layers. As you squeeze this, as you make it smaller, you end up with the single line. And this single line is the point in which you have the huge enhancement flow. And the mechanism for that is that the particles, they just layer and they flow like one line flowing. I might say that's not what usually people call single line diffusion, in which is not diffusive regime. This is diffusion regime. The only thing is that they are diffusion like that, one line after the other. That's what makes this go much more faster than it was predicted. Okay, so see you have similar mechanism. Again, I'm in dimensions units, so I think we could capture more or less what's going on inside. You have to notice that if you go to real water simulations, each blob that I have a blob is not a blob. You cannot see the single line because you have actually 4 molecules doing all kinds of random things. So the effective model is what allows us to understand what's going on. And why I'm saying that this is a good thing, and people are saying that's a good thing for getting more water. In fact, salt don't like get into channels. Why? Because usually the salt is hydrated, it's full of water around. And this 2 nanometers, 1.5 nanometers, that's the size of these nanotubes, you cannot enter with the sodium chloride plus a cup of water inside. So the salt, you have the tendency of getting out. What's the challenge, of course, is a challenge for the people producing the nanotubes. It's very hard to produce nanotubes that all the nanotubes have to be below 2 nanometers. Okay, they have all to be below 2 nanometers because if you can get a kink like that, you're going to have a problem in making these filters. But that's a proposition, very good proposition. There are people in companies trying to produce that, to produce filters of for desalinating water. Okay, we can also, but Marcia, that might be true for any material. You know, any material, if you put in nanotubes, nanotubes is such a new thing, they might all, not all, or only water, get huge flow when you put in nanotubes. So the thing we did, we are not going to test all materials, but the thing we did is that we tried the same thing, the same flow, if instead of using the 2-length scales, you use the Lennard-Jones. Okay, the blue is the Lennard-Jones. And you can see that the blue, the flow, normalized by the bulk flow, goes down as you decrease the size. There is no going up if you don't have the 2-length scales potential. So the 2-length scales, it seems to be fundamental to get this mechanism. Okay, but if you don't have salt, you know, if you don't have the sea close by, what other ideas we can have to get more water? There's another property that water have, is that water usually loves some materials, loves anything that have charges on it, and don't don't like very much things that don't have charges on it because of the polarization of the hydrogen bonds. And this beetle, that I found one day when I was doing nothing in the internet at night, looking for stupid things, I found this animal that's quite funny because they have this stick. You see, the back is some things like that, very small things like that. The top of this is made of a very hydrophilic material that loves water, like salt. And the bottom is made of very hydrophobic material. So what this material does is that takes the vapor air, the air in the vapor in the desert. In the morning, there's a lot of vapor because of the huge change in temperature, and they transform in liquid water. The liquid water goes down because it's hydrophobic, and just lean and drinks. Okay, so there are materials that we can also use. And you could think about a nanotube that will be part of the nanotube will be hydrophilic, and part of the nanotube will be hydrophobic. And then you can take the water or my two-length scales potential in the vapor phase and see if you can get that transforming the liquid phase, even though the temperature outside is saying you should be vapor. But then, because it's so hydrophilic, you form a layer and then go to the hydrophobic and get out in the way. No. This is... No, that is not going to show, fortunately. This is a GIF. Anyway, what we show in this system is that if you make it very huge, that's the here's the fraction of hydrophilic and hydrophobic. This is when I'm here, I'm saying that's poor hydrophobic. When here, I see poor hydrophilic in the middle. When it's half and half, that's the thing I need. And you see that the flow is quite bad, depending on the force that you're doing. If you do, I don't want to do force. Force is costly, so I want to be in this range and not in this range. If you do little force, you don't get very much flow. But if you make it very small, the tube, you can have the half and half and have a reasonable flow for the tube when compared with the bulk. So again, the answer to that kind of system, they have to do 2 nanometers kind of tube with part hydrophobic, part hydrophilic, if you want to transform water vapor into water and then flow it around. But there are a number of other materials in which you can play around. They don't need to do this difficult thing that's making nanotubes that I figure out because I went to experimental friend of mine, and I said, I want millions of nanotubes all aligned lower than 2 nanometers. They left to me and said, that's very hard to do. So I decided to look at other materials. And then there is this aluminum phosphide, in which they are of the order of nanometers, and they are part hydrophobic, part hydrophilic. So that's the thing we have been studying now, trying to put water in these materials. They are not as rigid as the carbon. So we have to, in the simulations, keep them not exploding with high pressures. It's quite difficult. But this is a material very cheap. It's a mineral, so it's very much easier to get than the nanotubes. There are other options easier to do. One is to do graphene, or to do nanocones, or to do sulfite of molybdenum. You make holes. Of course, you have to make holes here. Here you make holes, you have hydrophobic, hydrophilic. Here, if you make holes, you just have plain vanilla hydrophobic materials. And you can use that as osmosis or reverse osmosis procedure in which you have salt and water, and you can show that the water is going to pass. Let's see if this video works. No. Will not work. Anyway, they flow, so we end up having the possibility of using this structure that, again, is a nanometer, but they are much easier to being produced. So if I want to raise some conclusions, I'm going to say that water is very special, have a number of anomalies, but the ones that I'm going to fix lately is about the diffusion that increases when you put it in nanostructures confined, the enhancement of flow, and the transformation in vapor, in liquid, using super hydrophilic surface. Before I'm finished, and I think I will have plenty of time for questions, I want to apologize for the foreigners, but the next slide is only made for Brazilians. Sorry for that. And the reason is that at the end of last year, our government cut our funding in a half of the year 2010. And in March this year, they cut the half in half. So nowadays, we are living with 1/4 of 2010. And that's, you might say, well, less money, you have to cut. Unfortunately, the cut was uneven. Our cut was much harder than any other sector cut, include the farmers of my state, huge farmers, and the huge agricultural, and all the banks. They have all the debts forgiven. So I am in this, campaign for us to get at least the January budget back, means our 44% back to that. But I don't think, and that I am always aware, I don't think that's an occasional thing. I think that's something that's a global plan. And I am from a time, I'm old enough to be from a time in which you have a dictatorship in this country. And I thought I would never be back to a situation that I have to go to the streets. Unfortunately, last week, I have to take my T-shirt back from the 70s and say, I have hope, I need elections now. Thank you very much.
We still have time for a couple of questions or comments.
So I have 2 questions. One of them is, I know that this enhanced diffusion of water in nanopores is a very, very controversial question. And for example, in my lab, Lideric Bocquet, I don't know whether you know, he is doing these experiments to actually check whether this factor of 300 is true. And so they also do experiments, and then they do simulations. And so there's a big question of whether this factor actually exists. So I just wanted to know whether you have opinions on this. But the second question is, if I understand correctly, you did simulation on an effective model.
Yeah.
But this is, I think, one of the most important, hottest question. I mean, this diffusion coefficient of water in nanopores is one of the most one of the hottest subjects, right, in nanoscience. So I'm wondering, why didn't you do the simulation with real water molecules? I mean, you have all the technology to do it. You could write a fantastic paper. And so, and third question is, why did you find with this effective model, why was the enhancement factor so suspiciously similar to this, or not suspicious, but why was it so exactly this? Why was the numerical value of this enhancement factor just about the same as the one that you had in experiment?
Okay, it's not true. Okay, I pass very quick, but it's not. My effective have about 300, not just 900. So it's 3 times lower. Okay, I don't have everything. The fact, there's a huge discussion about that. And part of this discussion is that you see increase if you do one size. If you do another size, you see different. If you change, you understand, the length matters, the roughness matters, The type of nanotube matters. Most everything matters, and the numbers, they change from here to here. But they always are enhanced. You understand? The discussion is, then you change your water model, okay? I did one water model. I did another water model. Each water model, no, but first I did the plain vanilla model. In the plain vanilla model, I couldn't see, because I went to see what's going on inside. Because the waters are like that, because remember, each sphere is 4, and they're rotating, they are passing, they are going there. You'd have difficulties even to see the layers because of this, the bounding thing of water. So the water model depends. There's no perfect water, because the modern water models that we have today, I'm not talking ab initio, impossible to do ab initio, but the water models we have today, they are done for bulk, usually room temperature and pressure. And they give shitty dielectric constant. Shitty, it's better. No, the enhancement factors, they change. If you change the water model, they go to someplace else. They always are enhanced, but they don't see the layering. This up-down needs the layering. The only thing I want to bring is that people were coming with explanations from theory for the why is going on, saying things like, wow, it's the bridging and the quantum with the wall, with all kinds. When you don't know what's going on, you come very complicated. So I start as a joke, saying, if my model that's not quantum, is not even water, have it, is because the central part of the mechanism is lining. The other stuff comes later, okay? So now we have developed a model that gives the right dielectric constant. Because if I want to put salt, and then I have to make a sodium chloride that in water gives the right dielectric constant, because both things didn't exist, because nobody cared. But if I'm going to put salt and water passing through a roll that have a dielectric constant jump, huge, I need at least my models to be okay, you know. This here, the kink, they got that. From the experiments, they didn't know why the kink. What I'm claiming is that the kink is when you change from these 2 layers to a single layer, because we observe this correlation, okay? But if you don't see that, if you could look to the water, you're not going to see that. You need to somehow mark the clusters, like I could color the clusters somehow, you know, the tetramers, and follow the tetramers.
Any other question? Okay, thanks also for the last few slides. I think this is not only for Brazilians. I think all the world must be aware of what's happening here, this situation. Okay, let's thank our...